Okay, hi. So we will continue our discussion of Fourier series, and in particular, we will talk about convergence. Okay. So you can see the pointer. I hope no. Okay. So till now, we have been seeing how the Fourier series representation can be used to represent a periodic signal, and so now we will see uh, at some conditions for the Fourier series to exist. Okay, the question is, can all periodic signals now be represented by Fourier series? That is the question we will try to answer in this video. It can be seen that most practical signals can be represented by Fourier series. There are a few exceptions which we will cover during the course of this talk. So now let us represent the periodic signal x of t with n here there are 2n plus 1 Fourier series coefficient. Okay, so that we write it as xn x small n as capital N of t. So this means that rather than using all the harmonic components, we will use the first n components on either side to represent the given signal x of t. So now this representation of course will not be exact, so there will be some error. So x of t minus xn of t, this we write this as error, the error for the n, where n is the number of terms in the Fourier series. So and we also define the energy of the error, which is defined like this, and it can be shown that as your n tends to infinity, your E of n, that is the energy of the error, tends to 0. Okay, so essentially what this means is that the more and more terms you have in the Fourier series, the better is the representation you get to x of t through the Fourier series. So now let us relook again at the synthesis equation and the analysis equation of the Fourier series, which you must be familiar with these by now. So now there are some issues here which we have to be careful. First of all, this is these are the Fourier series coefficients. So what is the guarantee that this integral will converge? Okay, so there could be some signals for which this may not converge. Okay, especially now if you think if x of t is very big, then you may not converge. Although this is over one period, it still may not converge. The other thing is, when you do the synthesis part, when you represent x of t using the Fourier series coefficients, this is an infinite sum. This also need not converge to x of t. Okay, so these are the two things which we will be worried about. So one sure shot signal for which the Fourier series representation will exist is that which has the signals which have a finite energy in a given period. That is, if this squared integral is less than infinity, this energy term of x of t over a period, if this is less than infinity, then the Fourier series will exist. Okay, even though okay, so now in that case, if the x of t is a square integrable function, and this is my error E of t, which is written by x of t minus the infinite number of terms in the Fourier series, then the energy of the error is equal to 0. Okay, but energy of the error being equal to 0 does not mean that the representation from the Fourier series is equal to x of t at all times. What it means is that the energy of the difference is going to be 0. What that means, I will illustrate towards the end of this video. Now, associated with the Fourier series, there are these additional Dirichlet conditions which explicitly spell out what are the necessary conditions for Fourier series to exist. The first condition is that the signal must be absolutely integrable over a period. So that means if your x of t over a period, if you find out the absolute value and do this over a period, and if it is less than infinity, then the Fourier series will exist for such a signal. For example, this is an example of a signal which does not satisfy this first condition. Okay, so this is a signal which I have written as x of t is equal to 1 over t between 0 less than t less than or equal to 1, and this repeats. So that is the signal 0 to 1, it decays by 1 by t, and this repeats over every interval of 1. So this the signal looks like this, but this integral is not absolutely summable over this period because this integral does not converge. So this condition, this signal violates the Fourier series. So the Fourier series for this signal, particular signal, does not exist. The second condition is that the signal should have a finite number of maxima and minima over a single period. So for example, this signal here is an example of a signal which does not satisfy this condition. Okay, although this signal may be absolutely integrable, but it has an infinite number of maxima and minima in one period. So this is a signal which does not satisfy the second Dirichlet condition. The third Dirichlet condition is that the signal should have a finite number of discontinuities in a finite interval of time. So example, this signal has got series of steps like this, but this signal has got infinite number of steps. So this has an infinite number of discontinuities, and so this signal does not satisfy the third Dirichlet condition. Okay, so these are examples of signals which do not satisfy the Dirichlet conditions, and hence the Fourier series does not exist for these signals. So by looking at these example signals which we saw, we can see that most practical signals are not of this form. Okay, so for most practical signals, Fourier series do exist, and it can be calculated using either using the Fourier transform properties or by using the analysis and synthesis formulas. Now we should look at the interesting example of the Fourier series of a square wave. We have seen this earlier. So we have actually computed the Fourier series for a square wave in one of the examples, and we calculated also the Fourier series coefficients. Now let us see how the Fourier series coefficients can be used to represent the square wave. So this the main thing about the square wave is that it is not continuous, right? There is a discontinuity at, if you remember that example, it was between minus t1 and plus t1, there was a discontinuity at t1, and there is one at minus t1, and at t1. Okay, so now the square wave is shown in the background. In the foreground is the representation obtained using one Fourier series coefficient. Here in this case, n is equal to 1. Okay, so there is just one harmonic component is used here. So they are in your summation, the n is equal to 1. So it's just so you will get only one sinusoid. Now the if you use n equal to 3, the representation becomes like this. When n equal to 7, it becomes like this. So you can see that as more and more terms are added, it more and more approximates the square wave. And so this is n is equal to 79, I think. No, sorry, the n is equal to 79 is here, n is equal to 19, n is equal to 79. So you can see that as n is equal to 79, you can see that this pretty much approximates a square. But there is a catch. So you can see at these points, at the discontinuity points, you can see that there is a small offshoot. Right? So this offshoot is known as the Gibbs phenomenon. The reason for this offshoot is because of the discontinuity. The Fourier transform, the Fourier series does not exactly represent x of t at the discontinuities. Although we said that as the number of terms in the Fourier series increase, the energy of the error essentially becomes 0, but that does not mean that this signal xn of t, which is the approximation with the Fourier series, exactly matches x of t. So in particular, at the points of discontinuity, xn of t overshoots x of t by a small amount, and this the explanation for this was given by the American physicist Gibbs, and so this phenomenon is named after him. So this is a Gibbs phenomenon. So this is something which you must remember. Okay, so for whenever there is a discontinuity in the signal, you will have Gibbs phenomenon, and hence based on what you are trying to do, you should have sufficient number of terms in your Fourier series representation so that you can represent the discontinuity correctly. That no matter how many terms you add, this offshoot will not go away. That offshoot will be there, but the total energy across this will be, across the error will be, across the whole period will be 0. Okay. So that is one thing to keep in mind.